Okay, next we've got a double slit question involving light. It practices the formulae, and then in part C there's something else important that we haven't mentioned yet. So have a go at this one. And here we go. So we've got the distance from the slits to the screen here, and the slit separation here, and then the fringe separation we get from the diagram. We always measure across multiple fringes and divide in order to get a more accurate value. So that is 1, 2, 3, 4, 5 fringes is 7.4 millimetres, and so the distance from one fringe to the next is 1.5 millimetres, rounding to two significant figures. Put all of those numbers into the formula and you get a wavelength of 590 nanometers, so that's right for visible light, as a double check there. And then the last part of the question. If you cover up one of the slits, what will happen to the pattern on the screen? Now you might think, well, if we've covered up one of the slits, then our interference pattern completely disappears. All we're going to get is a bright spot on the screen. And you would be completely forgiven for thinking that, because the way I've described it so far, the interference pattern happens because of two wave sources, one coming from each slit. And in fact, the mark scheme appears to give you full marks for saying that. So the mark scheme for this question has a mark for saying that the pattern or the fringes vanish, a mark for saying that that's because now there's no interference from the light between the two slits, and a mark for saying that the light simply spreads out over the whole area. And that all makes it sound like there is no interference and there's no pattern on the screen. But what you in fact get is a pattern something like this. So a very wide, bright fringe in the middle, and then much fainter, smaller fringes on the outside. So it would be a good idea, if you haven't seen this before, to Google single slit diffraction pattern and just have a look at some photos of these. And so the mark scheme also gives you marks for, it says here, a simple description of the single slit pattern. So that's things like the bright fringe in the middle that's getting, so if I draw its intensity here, it's very bright in the middle and then it's getting dimmer to the edges here. And also of the smaller, dimmer maxima on the outside. And then it just says further features of single slit pattern. Okay, but I'm sure what you really want to know is, how on earth are we getting an interference pattern if we only have one slit? And the answer goes back to Huygens' principle that we mentioned earlier. Actually, when a wave passes through a slit, it's as though there are many, many, many waves all along that slit. So every place along that slit is its own little wave. And so you still get the interference pattern because it's the waves from one side of the slit interfering with the waves from the other side of the slit. This only happens if you have a suitably narrow slit. But this is what you get. It obviously looks different to normal double slits, but it's an important detail to add to your revision notes.